This problem-solving video looks at simple feedback. Now, first to remind you about what we're doing with these problem-solving videos. We're trying to demonstrate a simple technique for problem-solving which is generic enough to be applied for many different problems, and remind you that problems can often be open-ended and do not have a simple correct answer. So our proposal is to use a simple iteration through 3 steps. First of all, determine what the topic is, and then start by writing down what you know about this topic, and that could be formula or laws or assumptions, conventions, and so on. Then look at the information that you've been given and ask, can I use this information with what I know already in order to create new information? And finally, once you've done step 2, you might have generated some new information, and that might be useful in combination with step 1 to generate even more new information, and you will get some form of iteration. Now, key thing to remember is that problem solving is a skill that future employers want, and it's a skill worth developing. So step 1. This expects students to list what they know. So it's implicit, if you want to do problem solving, that you've got a comprehensive awareness, and here's a key word, competence, with a core knowledge that is relevant. If you're not competent in the core, you won't be able to do the problem solving. Students need to collect a list of what these tools might be and always have it to hand. So I would recommend that you always have to hand data sheets of key mathematical and engineering formula and laws, because you never know which ones you might need. So we're going to illustrate this process using a problem involving simple feedback. So here's the problem. Design a cruise control law for a mid-range vehicle. And you're given some very precise specifications. You want to settle to a target speed within 10 seconds. You want the speed to respond smoothly, and what that means is no oscillation or overshoot. You want to use throttle positions which are not above engine capacity if the speed changes are 40 miles an hour or less. You're going to assume that the engine can deliver 100 horsepower at mid-speeds and gears. And we're going to assume the vehicle is a typical family car, and thus it weighs about a ton. So first, let's start by saying, what do I know? Well, the first thing I know is that a simple car system, and I should emphasize the word simple, because this is introductory level, can be modelled as a mass damper. And a mass damper model looks something like this. Kf equals m dv dt plus bv. So Kf represents the force on the road delivered by the engine. M represents the mass, dv dt, the acceleration of the car, and bv represents the friction component. Now, for simplicity, what we're going to do is we're going to assume that this term K represents the maximum engine force on the road, and therefore the F represents, if you like, the throttle position, which can go between 0 and 1, 0, no throttle at all, 1, maximum throttle. Now, what else do I know? Well, a cruise control will select the throttle position, which then equivalently gives you a force on the road, automatically as a function of the error in speed. Okay? So, what we've got is the throttle position F is some function h of the error in speed, which I'm writing as r minus v. R, the desired speed, v, the actual speed. So that's a typical sort of control law, but I've not said what this function is. Now, typical function structures deployed for control are proportional and integral. So in other words, we would say that the throttle position is given by this law here. It's a proportional term kp times r minus v plus ki times the integral of r minus v dt, and that shouldn't say 5, that should say t. Okay? Now, if you turn this into Laplace transforms, you get a classic control law where the control law h of s is given by kp plus ki over s, and this is a pretty common control law. Now, what else do I know? So I've got the car model is given by the velocity equals k over ms plus b times f of s. I'm given the control law is kp plus ki over s, and hence I can use my knowledge of control and feedback systems to say that the closed loop system, or the speed response, is going to be given by this. the velocity is gh over 1 plus gh times r, where r is the target speed. And therefore I can work out the closed loop dynamics from this 1 plus gh term. So next then, let's ask, what information have I been given? So this just repeats what we got in the question. Reach the target speed within 10 seconds, respond smoothly, no throttle positions above maximum for 40 mile an hour speed changes, engine can deliver up to 100 horsepower, and the car weighs about a ton. So let's look at each of these in turn. First then, we need to settle to a target speed within 10 seconds. So what does that tell you? Well, your knowledge of dynamics of systems tells you, therefore, that the critical time constants must be of the order of 2 to 3 seconds. And that will give you a settling time of about 10 seconds. So if you then say, well, how do time constants relate to pole positions? It tells you the dominant poles have to be in the range minus 0.3 to minus 0.5. And for convenience, we'll use something like minus 0.4, which is in the middle, as a typical real part for your dominant pole. We want the system to respond smoothly with no oscillation or overshoot. Now, your knowledge of damping should tell you, therefore, that the closed-loop damping ratio should be greater than about 0.7, because as long as you're greater than 0.7, then you'll find that the overshoot or oscillation is minimal. So what does this tell you? Here's the closed-loop pole polynomial written in standard damping form, s squared plus 2z to omega n s plus omega n squared. First of all, we're told that the real part must be around minus 0.4. So if you put that in here, you see you get z to omega n is approximately 0.4. Or, in other words, if you went back here and looked at 2z to omega n, you'd get 0.8 in there. Now, if you assume, because often you can get higher gain that way, that the damping was on the limit, so it was about 0.7, then what you would get is this. Omega n is 0.4 over 0.7, which is approximately 0.6. You'll notice I'm using approximate throughout, and therefore my closed-loop polynomial will be something like this. And you'll see I've been very careful to write these requirements as approximate because they're ballpark, they're not exact. So we want a closed-loop pole polynomial something like s squared plus 0.8s plus 0.3. Next piece of information I'm given. I want to request throttle positions above engine capacity for speed changes of 40 miles an hour or less. So let's have a look. The change in the throttle value if you get a new error. Okay, so we assume that you've changed the target speed and you suddenly change the target speed by 40 miles an hour, so that's your error in speed. And what you'll find is the initial throttle value will be dependent just on the proportional term. And therefore, simplistically, you could write something like this. 40 times the proportional term kp must be less than 1, because the maximum throttle is 1. You'll see this is slightly simplistic in a few slides' time, but let's just go with it for now. Now, of course, 40 miles an hour is not in meters per second. So if I turn that into meters per second, you find it's about 18 meters per second. And I'm not using decimal places because that's rather pointless given we're being approximate throughout. And therefore, the actual condition you get is this. In order for your control law not to demand excessive throttle actions, then the proportional term has to obey 18 kp less than 1. What other information am I given? Well, I'm told that the vehicle is a typical family car and that it weighs about a ton. Now, a ton is about 1,000 kilograms. So if we assume that the engine delivers 100 horsepower at mid-speeds and gears, we can now work out roughly what sort of force we're going to get on the road. Okay, so a mid-speed would be something like 50 miles an hour. We also know that power is given by force times velocity. So if we do that, we can say Kf, that's the force delivered by the car, times the velocity equals 100 horsepower. Okay? So, however, I'm going to need to change all this into metric units to make sure I don't make silly errors before I continue. So let's do that. So, maximum power implies the throttle is 1. 1 horsepower is assumed to be about 746 watts. So what I get, Kf times V equals 100 horsepower in metric units gives me this. You'll see the algebra, so k times, and this is my change, okay, from from speed in miles an hour into speed per meters per second, and this is the change from horsepower to watts. And if you go through all that algebra, which I'm not going to do here, you see you end up with k is 3,500. Now again, you'll notice the use of approximate, because there is no point giving lots of significant figures in decimal places given the approximations we've done elsewhere. So what have we got? Kf is approximately 3,500 newtons, so the maximum force on the road is about 3,500 newtons. And what that means, given that the car weighs a ton, is the maximum acceleration is about 3.5 meters per second squared. So what do I need to do now? Because I've done an awful lot of different calculations, and you might say, where's all this going? You just seem to be generating new information for the sake of it. So what we do now is summarize what's all the information we've got, and once I've written this down, can I see a way forward? So we've got the closed loop dynamics, V equals GH over 1 plus GH times R. We know that the model is K of MS plus B. We know the control law is Kp plus Ki over S. We know that our target closed loop pole polynomial is approximately S squared plus 0.8S plus 0.3. We know that K, that's this K in the model, is about 3,500. And we know that our proportional term obeys this inequality, so in other words it's less than or equal to 0.05. We know that the mass m is about 1,000, and so we put this together, you see that there are still two unknown parameters. We don't yet know b, and we don't yet know ki. So before we can proceed to analyze this system, we need to do something about those two parameters. So let's see what other knowledge we've got. Well, the damping was not given to us. And therefore, you might say, well, I'm just going to have to estimate a reasonable value. In the longer term, what you might do is you might tell the person setting the question, you need to give me this information. You can't just expect me to guess. Right. Now, given this is a mid-range car, a top speed of around 100 to 120 would be reasonable. And so that you could assume that for f equals 1, v is about 100 miles an hour. Now, what does this give you? If you're at top speed, you get that the acceleration is 0. All the engine force is being used to drive friction. And therefore, you end up with this equation that all your engine force, which is K, equals BV. Now, if I turn V into meters per second, you will get an equality like this, that K equals B times 100 times 16 over 36. Oops, sorry, and that will give you B. What next? Next, we can form the closed loop transfer function and compare it to the desired closed loop pole polynomial. So we've stuck that B in into our model for G. What we found was B was about 80, and you'll see I've created my closed loop transfer function by substituting in for G, substituting for H, and you see, okay, it looks a bit messy. We'll do the simplification, and this is what you get, that your closed loop pole polynomial is this term here at the bottom, S squared plus 0.08 plus 0.18 times S plus 3.5 Ki. Now let's remember what was our target. I'm not too worried about what was in the numerator, and you can see here was our target closed loop pole polynomial. So you're asking yourself, can you make the actual closed loop pole polynomial equal to the target closed loop pole polynomial? And what do you notice? What you notice is you can't. You cannot actually do this, because if you look at this middle term, it's fixed, 0.08 plus 0.18. There was no variables in there. You cannot make that equal to 0.8. Why could we not do this? Because you'll remember there was a limit on Kp, and we put Kp at the largest value possible. And because of that limit, we cannot make the middle coefficient of the pole polynomial large enough to meet the time constant requirement. So remember, this value of 0.8 came about because we said we wanted a time constant of something like 2 to 3 seconds. And in essence, we can't meet this. And this is irrespective of what you choose for Ki. We can, however, meet a critical damping requirement. So, for example, if I said I wanted z to equal to 1, just to keep life simple, then I can say the actual pole polynomial is given as s squared plus 2 omega ns plus omega n squared. And if I solve that, you see I get omega n is 0.26 over 2, and therefore Ki is omega n squared over 3.5, which is 0.005. So you can choose Ki to make sure that the system has critical damping, but what you can't do is meet the time constant requirement because of the limit that you set on Kp to make sure that you didn't overactuate the throttle. So what do we get? What we've got is an assumption is incorrect, or the requirements we were given need to be modified. So there's two possibilities. We've made some assumptions as we went, and you could go back and you could say, well, were some of those assumptions incorrect? Alternatively, we would set requirements which were just not realistic and cannot be met. However, we can investigate the system a bit further to try and understand why we've got to this impasse. So how might we do that? Well, the most obvious thing to do is to sketch some of the responses with the design that we've got so far, the selected Kp and the selected Ki. So you'll see what I've done here is I've done a speed change from 50 miles an hour up to 90 miles an hour, and you'll see the difference there is 40, so we're pushing things to the limit. Now, if I look at the throttle, what do you notice? The initial throttle is 1.4. It's a lot bigger than the maximum throttle position down here of 1. So the first thing we notice is not only does our control law not deliver the time constant that we wanted, it's overactuating the throttle. It's not meeting one of the specifications we set. And you might think, that's odd. I thought that we'd insisted on that. But there's a reason for this. Okay, now we can see the settling time is around 15 seconds. So it's not too bad. We had targeted 10 seconds. 15 seconds isn't a lot slower, so you might say, well, I'm almost happy with that. Okay, but Kp is too large, and the reason it's too large is because we assumed that the only part of the throttle during transients was the bit coming out of the proportional. But in practice, if you understand PI control, you'll find that the integral contains a history term, and if you were already at 50 miles an hour in steady state, your throttle would have started at 50%, and that would have come from the integral term. And therefore, when you've got a 40 mile an hour speed change, as we've got here, you've only got half the throttle left to play with. And that's why we've overactuated, because we've said 40 miles an hour uses the full throttle, full 100%, but you've only got 50% available. Okay, so this control cannot be implemented. However, what could you do? You could say, all right, let's assume that I put in some saturation. So you'll see here, I'm going to saturate the throttle. So if the control law says demand a throttle which is too big, I'm not going to allow it. I'm simply going to say, no, you've got to stay at 1, because that's all you can deliver. And let's look at the responses we get. Now you'll see, because the throttle has saturated, I've got a slower response from 40 to 80 than I had from 0 to 40. But it's still not too bad. You still say, well, that's reasonable in terms of what I can expect. Okay? So despite the overshooting the throttle, you could argue that this tuning is still reasonable. Okay? It still gives quite nice responses in terms of what's achievable for this car. And the other thing you might say is, look, if I want 40 mile an hour speed change, then it's normal to overuse the throttle, to put the throttle right to the floor, and therefore to get what I can see here, which is some saturation. And therefore, I should not view this saturation necessarily as a negative, but as an indication that this proportional control, or PI control law, is actually driving the engine reasonably hard, which is what I would want. So, my conclusion is, although this PI does violate constraints in some cases, I think it gives reasonable behaviour. And that's just another look at the scenario. If you were at 50 miles an hour, about half the total engine force is already consumed with drag, and therefore you've only got 1800 newtons left for acceleration. And what that means is the maximum acceleration you could get at 50 miles an hour is about 2 meters per second squared, not 3.5 or 4 meters per second squared. And clearly, an acceleration of 2 meters per second squared, and that's at 50, is going to be too small to give you a change of 18 meters per second in 10 seconds, because the faster you go, the slower the acceleration you can get, because the more of the engine force is used up on drag. So what's the conclusion? Clearly, this engine is not powerful enough to deliver the desired dynamic response, which was a settling time of 10 seconds. You can't do it. You need a more powerful engine to get that at higher speeds. So this video has given an example of problem solving, and a simple approach involves some key steps. First, ask yourself what topics might be involved, and what should I know about this topic, and you'll notice we then just wrote all those things down. Next, look at the information you've been given, and then ask how might you use this information in combination with what you already know. And this is key. It's bringing into the question what you already know, which makes the problem solvable. The question won't tell you everything. It won't tell you how do you find a closed-loop transfer function. It won't tell you how do you define a critically damped system. It expects you to bring this knowledge with you and introduce it where you need it. So that's why step 1 is so critical. Think about all the information you might need, and then when you need it, you'll be able to use it. Finally, you'll see once we've put 1 and 2 together and generated all our data, only then did we start saying, what have I been asked to do? We didn't jump to the purpose of the question too quickly, because we might say, I haven't got a clue. But once we've written down all our information, you suddenly think, well, actually, that's not too bad. I can do that with all the information I've got. And the other thing is it's okay to be critical of the assumptions or requirements that you've been given, because that might be the purpose. The person writing the question might want to be asking, can you think? Are you really an engineer? Can you be critical? Can you propose sensible changes, etc., etc.? So, finally, it's shown that real problems might not have clean analytic or even unique solutions. And what you've got to do is justify the choices you make or the approximations you make, and so on. And remember, sometimes the requirements set cannot be achieved, and the examiner might be actually expecting you to demonstrate this.